what the question is. The question is not calculate this or that. The question is just, okay, here's a solution. We're going to electrolyze it. What happens at the anode? What happens at the cathode? So we'll have to use this table. There's two examples here. I have potassium chloride solution, then I have zinc iodide solution. Let's do this one together, and then I'll ask you to try the zinc iodide. Okay? Oh, you... This did this to me last hour, too. I had to restart the computer. It's not interacting with me. Okay, so I'll have to do this on the whiteboard. When you have 1 molarity of Kf, the potassium is positive 1 charge, the fluoride is negative 1. The question asks what happens to the cathode and the anode. So let's take on the anode first. That's what we did in the last example. The anode means that oxidation is occurring. So you have to ask yourself, does potassium oxidize? Does fluoride ion oxidize? And does water oxidize? So which of those three are possibly going to oxidize? And what is the answer? Can potassium oxidize? Potassium is positive 1. Can it go higher than positive 1? Nope. Can fluoride oxidize? It's got a negative 1. Can it go up? Yes, to F2, to neutral fluorine. So for fluoride ion to oxidize, that means that we're going to need that very first, look at your table, the very first equation, a half reaction on there. Remember, we're talking oxidation, so you got to turn it around. It's two F minuses, and I'll use a better marker than that. 2 F minuses yields F2 plus 2 electrons. And the oxidation potential is negative 2.87. Thank you. Now the other candidate here is it's not potassium because potassium can't oxidize. The other candidate is water. And here's something I would suggest to you because you're going to have to do this, or you don't have to do this, but you're going to have to look for water more than anything else that you look on here. So let's just do this right off the bat. If you have a highlighter, I would suggest that you highlight the reduction of water, which is the one that's negative 0.83 over here where my finger is. It's right there. Find the negative 0.83 reduction of water and highlight it. Again, you're going to have to look for water more than anything else. So to have it highlighted and have your eyes go right there will be handy. You'll see. I would also suggest that you highlight the oxidation of water, which is over on the left column. That's the one that's almost exactly halfway down. The 1.23. Highlight that 1.23 and the negative 0.83. And you'll be glad to have done that. Okay, so one of them we're going to need right now. Which one do we need? We're talking about the anode here. I should even write this up here. Anode. So our choices in the anode need the fluoride oxidizing, or I need the negative 1.23. It's the water oxidizing. 2 H2Os yields O2 plus 4 hydrogen ions plus 4 electrons. Now the oxidation potential of that one is negative 1.23. I know I've just cut off the angle on this for you guys over there. I'm sorry about that. But the oxidation potential of fluoride is negative 2.87. Oxidation of water is negative 1.23. So the question is, what happens at the anode? Well, it's either one of these half reactions. It has to be the water. Because water's oxidation potential is more positive than fluoride's oxidation potential. In fact, there's nothing worse at oxidizing than the fluoride ion. It's got the most negative oxidation potential you can have. Okay, now at the cathode, we have to do the same thing. Consider what in this solution is going to reduce. Can the potassium ion reduce? It's positive 1 right now. Could it reduce? Yeah, potassium could. Yeah, it's positive 1. The oxidation number could come down to 0, and you'd have potassium metal. So yes, potassium is a candidate. Could fluoride ion, which is a negative 1. You ever see fluoride with a lower oxidation number than negative 1? No, doesn't ever form negative 2 or negative 3. And then there's water. There's always water, because water could do either. So we'll do the potassium first. Find the reduction of potassium on here. I'll point to it way down in here. It's like the 5th from the bottom. No, it's actually the 2nd from the bottom. Sodium is 5th from the bottom. So, yeah, the potassium ion is not too interested in reducing. Potassium reduces to make potassium metal, and the reduction potential on that one is negative 2.92. I would say that means the potassium is quite resistant to reducing. And then the water molecule, the water reducing, that's the one that you highlighted over on the left side. The left side? No, it's the negative 0.83. It's the one on the right side that you highlighted. It's the water. And that's reducing into, it's got to add 2 electrons to it. It's going to make hydrogen and then 2 hydroxide. So the reduction potential of the water is negative 0.83 volts. This is a lot of work and it's confusing, isn't it? So once you have the possible things that could reduce and what the reduction potentials are, then just take the one that's more positive, which is the negative 0.83. It's not positive, but it's more positive than negative almost 3. And so what we find is that the 2 things that I have put the green boxes around, that is what happens when we use an electrolysis setup with 1 molar potassium fluoride. So once again, we never used the potassium in either half reaction or the fluoride ion. It was water in both cases. The water oxidized at the anode, the water reduced at the cathode. Now, is it water every time? No. It's not every time. So I'm going to ask you to try to do the zinc iodide. Let me do that. So I can let me write. So you have a solution of zinc iodide. You got zinc ions, iodide ions. This is I negative. Don't be tempted when you see the I2. It's not iodine the element. It's iodide ion. And then you have water molecules because it's a solution. You know it's a solution because it says 1 molarity. What happens to the anode? What happens to the cathode? I'll give you a couple of minutes. Enjoy. See you. Able to come up with what oxidizes and what reduces at the two electrodes? Great. Now in this case, I wanted to make sure that we did this one because the first two examples, it wound up just being water at both anode and cathode that changed. But in this case, it's not. Between the iodine oxidizing and the water oxidizing, the more positive oxidation potential is the iodine. Yes? So we would have elemental iodine being made at the anode. So whatever electrode is in the solution at the anode, it would start being covered with iodine. And then at the cathode, looks like between these two things, the more positive one is zinc. So there would be zinc coating the electrode on the cathode side. All right, you think you can do that? Now, I'm going to warn you. When you start doing the exercises for this chapter, most of the exercises are going to be really easy. I mean, sketch the cell, you've done a bunch of those, and you know what direction the electrons flow, and you can label stuff and do the line notation. And then you'll do the Nernst equation, finding the cell potential even when it's not a standard condition. It's pretty easy. And then you're going to get to these questions where you don't even have to do any math. It's just what happens to the anode, what happens to the cathode. I think these are the most difficult of all the problems. People have more questions about these than anything else. So if you think that, oh, okay, yeah, I feel like I have it, try it. Try it on your own. It seems to get people more than anything. All right, so I only have one other thing left with these. And that is sometimes, oh, thanks. Yeah, I think I could go for that. Thank you. Sometimes we're going to need to calculate how much, especially at the cathode where something is reducing, like if we can reduce a metal on a cathode, in this case, that's what we're doing. This example has the iron and zinc reaction. Spontaneously, the zinc should be sending electrons over to the iron. If we looked at what the cell potential was, if we wanted to make a cell out of that, the zinc would be oxidizing, the iron would be reducing. However, we got a power source here that's pushing the electrons back the other way. So what's happening here is this zinc is getting forced